Hi, everyone. Uh, this is Water as a Resource, Practical Applications of GIS and Remote Sensing. I am Josiah Thomas. I am from Denver, Colorado, born and raised pretty much my entire life. Went to school there and all. You'll see that soon. I specialize in water infrastructure asset management, GIS and remote sensing for climate resiliency, technical assistance for water and wastewater systems, funding and policy strategies for sustainable water management. My headshot on the right. That's me. To give you guys some context, I decided that it's a good idea to go over my background. I started at the Colorado School of Mines. I studied geophysical engineering, among other topics, but most of it was geology, geophysics, civil, and back to geophysics. That was my track. The skills I developed were Python, C++, GIS in the Esri suite, SQL, data processing, seismology, mapping, and sampling. My experiences included collaborative research, software development for seismic wave scattering. I also published a paper with one of my professors. On the right, you'll see we have a tree diagram out of Colorado School of Mines. I came out with three really most important realms of understanding, which are geophysics, energy sector dynamics, GIS, and data science. This obviously led me to my early professional roles, which were mechanical integration engineer at Marathon Petroleum. My focus there was asset management, asset performance management software, and petroleum processes. The skills that I developed were mostly Excel, petroleum engineering processes, and data management. That then led me to EdCon PRJ, where I was the processing technician for marine geophysical data processing, which included gravity magnetic tandem to seismic data processing or collection. I did the quality control, I did the quality processing, I pushed it out to the user or the end user, and I finally created a report. That was the general workflow there. I used Global Mapper, Oasis Montage, GIS, and Python to accomplish these goals. The skills I developed were large scale data processing, cross functional teamwork, among other things. That's what I have listed. On the right, you'll see we have more expansion into the tree diagram. From geophysics, energy sector, and GIS and data science, we were able to transition in more into the energy transition work, geophysical data analysis, and oil and gas asset management. This then leads me to my transition and reset. I took a career break. It was what I consider a post COVID adjustment where I took some part time jobs. I reflected on myself and what I wanted to do in my life. I decided to pivot from oil and gas into water, sustainability, and GIS driven problem solving, which leads us to today, where I focus on water and sustainability leadership. As project and funding specialist with the Colorado Rural Water Association, my role is to empower rural water systems through funding, training, and strategy. The achievements, some relative achievements, are I've trained over 50 systems, I've published articles, efficiency improvements abound. The skills I've developed are in line with funding, asset management, technical assistance delivery, and client relations with GIS water integration. I also have been working on a GIS project where I map municipalities. It's not necessarily an entrepreneurial venture, it's more of just an idea that I have to share. It applies GIS, normalized difference vegetation index, and parcel level mapping to irrigation and equitable access to water as a resource. The skills I've developed within this are machine learning, remote sensing, UAVs, data validation, and startup leadership. The focus was to translate data into actionable insights and provide partnerships with local and federal entities. Obviously, it goes hand in hand with my current position. While it's not making me money, it's making a difference. On the right, you finally see the solutions to sustainability and water resources. This brings us to other facets, which is generally what you find in the current iteration, that your directions are many. Of course, you have to discretize it into more manageable pieces. That's where I'm at. Water equity, smart irrigation, consulting, sustainable technologies, and entrepreneurship. Now this brings us into the critical aspect of this presentation, which is why is water as a resource such an important topic? Water is the most critical resource probably on our planet. It supports communities, ecosystems, and industries all throughout. It is essential for health, food security, and economic growth. Why do change and innovation matter? Aging infrastructure and weather extremes threaten stability. Data-driven management improves sustainability and resilience at the end of the day. On the right, we'll see the current drought monitor for the entire U.S., which even includes Puerto Rico. They obviously have been mapping it for a long time. On this, the most recent data poll in the that I took, it 27.7% of the um, land has been classified as in drought. Whether that's moderate or exceptional drought, obviously, there varies. Um, there is significant drought, and people are having to react. This leads us into the critical issues in the water industry. We have, first and foremost, aging water and wastewater systems. Many pipelines and treatment processes unfortunately exceed 50 to 100 years of service life. Leaks, contamination, and structural failures naturally increase with age, leading us to recognizing this as an outstanding problem. The example that I chose to example was the Baltimore water crisis in 2022, where decaying pipes led to E. coli contamination in the drinking water. That then leads us to lack of preventative maintenance, which goes hand in hand with aging infrastructure. Deferred upgrades lead to catastrophic failures instead of gradual improvements. The example I chose was Jackson, Mississippi water crisis in 2022. Decades of neglect resulted in total water system collapse, leaving thousands without water. Of course, I wasn't there. It is documented. On the right, you'll see an image of an empty water tank. I know not many water tanks are filled with graffiti, which is why this is obviously AI generated. I thought it was an interesting topic just because I think that water tanks, even in times of drought, can be utilized for maybe communal practices or different community festivities. I've thought a lot about it. All you need is ventilation and proper access. So, a little anecdote there on obviously secondary uses of certain water resources, specifically tanks in this case. Now, this leads us to another critical issue, which is extreme weather exposure. Infrastructure is often designed for outdated weather conditions and fail under modern extremes. The example that I chose is the Texas winter storm of 2021. Power grid and water system failures occurred due to poor insulation and lack of preparedness. This also goes hand in hand with improper implementation and cost cutting. Lack of enforcement of building codes and infrastructure best practices lead us to reactive maintenance. We don't want to react, we want to respond, and we want to proactively plan so we don't have to react to these problems. The example, I think we're all familiar with the Flint water crisis. Proper corrosion control led to widespread lead contamination. Not the most fun topic to really talk about, so I'm going to continue on. The image on the right, again, AI generated. It goes to, I wanted to demonstrate that there's a lot of infrastructure under these main highways, especially in between cities. I just thought it was an interesting example to include. Obviously, not necessarily the most intuitive example because it's AI generated. It shows the complexity. Now, the final slide for critical issues. We deal with funding challenges every day. It's a main part of my job. I know how important it is. But at the end of the day, aging infrastructure requires massive investment. Self-funding is often inadequate. So many water utilities rely on outdated pricing models, leading to financial instability and improper rate setting. Federal and state grants also exist, but are highly competitive, leaving small utilities at a disadvantage. Deferred maintenance creates a cycle of crisis response, increasing the long-term costs. The example isn't necessarily a specific example. Many struggle to upgrade water systems to high upfront costs and limited local revenue. Obviously, again, goes hand in hand with workforce retention and labor shortages. Aging workforce. Many water operators are nearing retirement with few replacements in the pipeline. High turnover rates in rural and underfunded water systems exist due to low wages and high job demands. Finally, lack of training and career pathways. Water sector jobs require specialized skills. Many communities lack workforce development programs. The example that I choose to reference is the AWWA report in 2022 found that over 50% of water utilities are struggling to fill critical positions, threatening long-term operational stability. If you have that experience, let me know. This brings us to weather-related remote sensing. I wanted to bring in a little bit of remote sensing to keep you guys at least not in the doom and gloom. The variable sea levels and coastal flooding, it's pretty easy to measure that nowadays, especially with satellite altimetry, which measures sea level rise. Synthetic aperture radar maps tidal flooding extent, even on sunny days. Optical remote sensing, aka taking photos, tracks coastline retreat and saltwater intrusion. Now, this also goes hand in hand with variable droughts and water scarcity, specifically the Colorado River Basin. GRACE satellites, which are the Gravity Recovery and Climate Experiment, detect groundwater storage decline through gravitational means, obviously. The Normalized Difference Vegetation Index monitors agricultural stress from water shortages or water surpluses. It's really useful for that because you get to see the health and the prevalence of your vegetation. Thermal infrared measures surface water temperature and evaporation rates. And microwave radiometry tracks soil moisture and conditions across the basin. On the bottom left, you will see a visualization of the variability of tides and weather pattern or ocean patterns. I figured I found that on NASA's website. The next image shows the upper Colorado River Basin. It's the Colorado River Basin. It shows that in the last 25 years, there has been significant removal of the groundwater in the Colorado River Basin. Very concerning to see over 12 millimeters per year lost in certain areas. We're drawing water. We need water. So let's make some plans to counteract this groundwater extraction. Now that we've seen remote sensing, let's talk about the power of GIS and remote sensing. They revolutionize infrastructure and resource monitoring. It keeps water systems resilient under stress through data. It connects real-time and historical data, helping utilities track change over time. It enables predictive analytics and smarter decision-making processes by supporting proactive planning and not just crisis response. GIS and remote sensing provide for smarter, more resilient water systems. This leads us into what is GIS? Methods for capturing, managing, and analyzing and visualizing location-based data. Obviously, the key here is location-based. What it does, it combines software, hardware, and data to reveal spatial patterns, relationships, and trends. Why it matters. Essential for managing water resources and making data-driven decisions. How else are you going to compile spatial data other than a map? We go into types of GIS data. Unfortunately, this is a previous iteration of the project. Rasters are the top table. They are grid-based data representing continuous surfaces. They are made up of cells, aka pixels, which we're all familiar with what a pixel is, each containing a certain value. The examples of this could include elevation models, topographic models, land cover and vegetation, or precipitation and temperature maps. These are generally what you're looking at with either compiled images or with collected images. Vectors, however, are coordinate-based data representing discrete features. They are made up of points, lines, and polygons. Examples could be wells or hydrants, which are points, rivers, roads, pipelines, lines, watersheds, parcels, and lakes, which are polygons. On the right, the visualization just kind of shows you the rasters on the left, the vectors on the right, points. You see the difference now. Then what is remote sensing? How do we determine how to use it? The remote sensing is the science of obtaining information about the Earth's surface without direct contact by detecting and analyzing energy that is emitted, reflected, or returned. There are two forms of remote sensing. Of course, there are even more caveats in between each. There's passive sensing, which is measuring naturally emitted signals, naturally emitted or reflected signals. And active sensing emits signals and measures the return. The benefits of both are prominent. They obviously both have detractions as well. Within passive sensing, the benefits are that it uses natural energy, it has large scale and long-term monitoring. Many data sets are free and publicly available and cost effective for global coverage. Benefits of active sensing are that it works day or night in all weather. It is high resolution and precise 3D mapping. Of course, it depends on each individual form. In general, you can say that these are all true. It can penetrate canopy, soil, or water. It enables real-time or near real-time analysis, of course, in the event of a disaster or something of the like. The limitations of passive sensing are that obviously it's limited by sunlight or the direct source of radiation, so you don't necessarily get any data at night, any optical data at night at least. The atmosphere can also block signals. There's lower spatial and temporal resolution. Temporal meaning time-based measurements. The limitations of active sensing, on the contrary, are the equipment is expensive and operations are as well. It requires more power and expertise, oftentimes requires contracted missions. This takes us into how do we measure? What are the tools we're using to measure with? The first and probably the most prominent is terrestrial or ground-based measurements. Most of us have seen this at this point. It's what most of the other GIS presentations are at this conference. It is terrestrial. It is ground-based, which you have field sensors, LiDAR, GNSS stations, SCADA systems. I'm sure you've all been hearing these words in the last couple days. The pros are that it's high precision, real time, and also is direct validation. The cons are that it has limited spatial coverage and higher maintenance through time. You're dealing with 15 sensors rather than a single sensor most of the time compared to the other forms of collection. This takes us to airborne, drones, aircraft. The uses are UAV, aka drone imagery, aerial LiDAR, multispectral cameras. Of course, they're all more or less interchangeable. The pros are flexible, medium to high resolution, and also very task specific. Let's say you want to map your municipality. Put an airplane or drone over it, map the entire thing in a couple of days, and bada bing, bada boom, you got a data set. The cons are obviously cost, regulations, and very weather dependent for surveying. This takes us finally to orbital or satellite collection. The uses are Landsat, Sentinel, MODIS, commercial satellites. It's obviously all satellites. Most of these are either governmental or private or commercial. The pros are that you get broad and global coverage, long-term archives, and regular updates to your data. The cons are that obviously it's lower resolution depending on the sensor. There can be atmospheric interference, sometimes costly for high resolution data. This takes us to the passive sensing cheat sheet, where we have passive sensing methods, how it works, applications, and example sensors. The order obviously isn't necessarily prevalent. They are all very important. We'll dive into optical remote sensing. It captures reflected sunlight from Earth's surface in multiple wavelengths. It can be used for land use classification, water quality monitoring, and drought assessment. The examples could be Landsat, Sentinel-2, MODIS, Google Earth. They're all, I would say almost every satellite up there has optical sensing. It's just at what resolution and at what temporal scale. We then have thermal infrared sensing, which measures naturally emitted radiation from surfaces. This could be water temperature mapping, urban heat island studies, or drought monitoring. Landsat 8, thermal infrared sensing, and ASTER are both satellites that would provide you this information on a global scale. We then have microwave radiometry, which detects naturally emitted microwave from Earth's surface. This could be used for soil moisture detection, sea ice tracking, or precipitation monitoring. I'm not sure what the satellites are on this one. I forget what the SMAP is. Obviously, microwave aperture productivity. It's hard to remember all the acronyms in remote sensing and GIS, geophysics, water. Lots of acronyms. This then brings us to solar radiation and albedo measurements. I am curious if you before this presentation knew what albedo was. Albedo is the amount of sunlight reflected by a surface. Obviously, Earth's albedo is the amount of sunlight reflected by Earth's surface. This can be used for climate studies, glacier monitoring, and agricultural monitoring as well. The Ceres and the MODIS satellites are both excellent for this type of analysis. Finally, we have atmospheric sensing, which analyzes how sunlight is absorbed, scattered, and reflected by gases in the atmosphere. This is great for air quality monitoring, cloud cover analysis, and atmospheric gas tracking. The OCO2 and the tropomi are both probably the best forms of data in terms of what you're able to access publicly. This brings us to the active sensing cheat sheet. Obviously, take a picture. This one is a lot more information. We're still going to try to dive into it. The active sensing method, we've all heard of and probably are familiar with LiDAR at this point, which emits laser pulses and measures the return time to calculate elevation and structural features. This can be useful for topographic mapping, forestry management, infrastructure monitoring, and bathymetry. I'm not going to go into the individual sensors. Take note if you're interested. Again, these are more often personally contracted than publicly available. We also have radar, radio detection and ranging. You have a source of radio waves. You measure the pulse of the reflected signals to detect the objects or surface properties. Again, all of this is really dependent on surface properties and what the interface between the air and the medium look like. Land deformation analysis, precipitation monitoring, soil moisture detection, and ice sheet tracking are all possible through this form of measurement. This takes us to sonar, sound navigation and ranging. We have sound waves to measure underwater features by analyzing the echoes. It's all echoes. It's all echoes. That's what you have to remember. Either reflections, echoes, whatever you want to call it. This can be useful. We're all familiar with seafloor mapping, submarine detection, and fishery monitoring. I am curious if y'all have heard about ground penetrating radar. I think that it is among the most important forms of infrastructure monitoring that we can potentially apply. It is also the most explicit form of geophysics in this list. Obviously, I'm partial. GPR emits electromagnetic waves into the ground and records reflections from subsurface materials. This can be useful for pipeline mapping, archaeological surveys, and geotechnical engineering. Laser altimetry is essentially LiDAR. It's using laser pulses to measure land elevation and ice sheet changes. I could have sworn I deleted that. But this is specifically useful for ice sheet and glacial monitoring and land subsidence detection. I think laser altimetry is better for individual point surveys rather than LiDAR being useful for regional surveys, if that makes sense. We then have scatterometry, which uses microwave signals to determine surface roughness and wind speeds. Obviously useful for ocean one monitoring and sea ice mapping. Finally, we have fluorosensing, which I think we're all familiar with the fluorosensing of chemicals in waters. So it emits UV light and measures fluorescence from natural or artificial compounds. This is great for water quality monitoring and air pollution tracking. What does all this mean for us? What does it mean for water industry professionals? The perspective for this is we have two sources of data. We either have publicly available data or collectible data. Publicly available data, obviously freely accessible, broad coverage, and useful for system-wide planning. It may lack resolution. It could have too complex of data formats, which require explicit GIS and remote sensing expertise. Also has limited timeliness, where updates may be lagging behind real-world events. The opportunities with collectible data is that it's tailored to local system needs, aka meters, SCADA, UAV imagery. It has high resolution and real-time inputs, You control the inputs as well, which is a favorable aspect. It enables targeted decision making overall. Unfortunately, there are high costs of equipment, sensors, and staff training. Data integration also presents a challenge with legacy systems and siloed records. Concerns around data ownership, privacy, and cybersecurity are also paramount. This leads us into the practical applications of GIS and remote sensing, where we're going to dive into each individual topic and see how we can potentially implement these technologies. Infrastructure monitoring and management play a critical role in water resource management, from pipelines and treatment facilities to reservoir and stormwater systems. GIS and remote sensing provide advanced tools for monitoring, analyzing, and optimizing infrastructure performance in real time. These technologies help improve asset longevity, reduce operational costs, and enhance resilience against failures and environmental hazards. Asset mapping and digital twins. Infrastructure inventory to start. Digital maps of distribution systems, stormwater networks, and treatment plants and pumping stations centralize asset information. This enables real-time tracking of asset age, condition, and maintenance schedules, which I'm sure we can all appreciate at some level. This also forms the digital twin aspect, which combines GIS, sensor data, and predictive analytics to create a virtual model of water infrastructure. It enables real-time asset tracking, leak detection, and resource management, among many other things. Leak detection and structural health is another element that I wanted to focus on. You have thermal imaging, LiDAR, and synthetic aperture radar to help detect leaks and underground pipe failures. GIS-based hydraulic modeling also optimizes network efficiency and water loss. LiDAR and ground-penetrating radar track movement and structural shifts in critical infrastructure as well. Bridges, reservoirs, dams, and treatment facilities all benefit from the temporal analysis of structural characteristics. Drought and variable weather adaptation. Droughts are among the most severe climate-related disasters impacting water availability, agriculture, and ecosystem stability. GIS and remote sensing provide for essential tools to predicting, tracking, and mitigating drought conditions, allowing for better resource allocation, early warning systems, and long-term climate adaptation strategies. Drought monitoring right off the bat. We have satellite-based vegetation indices. The NDVI and the EVI assess plant health and water stress levels. It helps identify drought-prone areas by detecting anomalies in vegetation cover. Soil moisture monitoring also is achieved by passive microwave sensing. I just don't think this is necessary. Whatever, we'll keep going. I wish that this stuff was going to be useful. Unfortunately, it just make people angry. Climate and weather data integration. GIS integrates historical precipitation, temperature, and atmospheric data to create weather probability models. Hydrological models also integrate multiple forms of remote sensing to simulate watershed responses to drought conditions. It helps utilities and policymakers develop proactive conservation strategies. Flood risk and infrastructure planning. I don't want this to be over half an hour, so I'm just going to let you look at it. Let's get into the practical advice. Where do we determine where we're supposed to be, or how do we determine it? Start with what's free. Leverage publicly available data sets. Use these as baselines to understand regional trends before investing locally. Pilot collectible data. Begin small. Deploy sensors or UAV imagery in one pressure zone or one pilot area. Test integration with SCADA or GIS before scaling across the system. Invest in skills, not just in tools. Train staff in GIS and remote sensing basics. Reduce reliance on outside consultants. Build partnerships with universities or regional water associations for knowledge transfer. Have a plan for integration. Design SCADA or design data collection with the future integration in mind. SCADA, billing, GIS layers. Make sure it's able to integrate cleanly and safely. Standardize formats early to avoid siloed data. Finally, balance cost versus value. Public data provides for low cost and broad trends. Collectible data, higher cost, high resolution. We have both on both sides. Use both strategically to inform rate studies, asset planning, and resiliency strategies. Finally, be the grassroots effort. That's all I have to say.